We're very happy. We're very happy to have Rajeev from IHES, and he'll be giving us today's string seminar. He's going to be talking to us about bootstrapping the 3D Ising stress tensor. Please.
Okay. Thank you, Shanmugapriya, and thank you all for coming here on Friday afternoon to have a chance for me to discuss some exciting work with you all, and for the invitation to come out and speak. So I'm going to be presenting some of the latest work in the numerical conformal bootstrap, in particular studying our favorite topic, the 3D Ising CFT. And this talk will be based on some joint work with all of these authors that appeared in the archive a couple of months ago, and as well as some ongoing and unpublished work. So before I get into the CFT or the Ising CFT, I wanted to just very briefly say a few words about the bootstrap philosophy, just so that we can all be on the same page on this front. So the point of view of a bootstrapper is, instead of constructing some specific example of an object, we instead use axioms and consistency to find out where the objects aren't in some definition of a parameter space. And I'm being purposefully vague here because I don't want to make it sound like the only bootstrap there is conformal bootstrap, even though the rest of this talk will be all conformal bootstrap. And so the axioms that we use are, for example, physical principles like unitarity, locality, analyticity of correlation functions, symmetry. These are rock solid assumptions that we hope to be true always. And we can use these in many different ways, both with pencil and paper and with numerical techniques. And in the realm of numerical techniques, oftentimes the formula is to take a consistency condition and formulate it into some sort of a positivity problem. And a positivity problem is something a computer can understand and can solve with optimization techniques, and therefore we can get some nice results. And in doing all of this work, we can learn lots of very interesting paper and pencil analytic things, even from the numerical work. And this slide is actually just an advertisement for Dalimil Mazach's very nice lectures on mathematical methods in the Bootstrap at IPHT in France. So if you go to this YouTube link, you'll be able to see these lectures. He goes through everything from Gaussian integrals to sphere packing, and with some CFT thrown in the middle. And that's a very nice set of lectures. So there's that. So, of course, in this talk, we're going to be talking specifically about conformal field theories and the conformal bootstrap. So first, we need to define what a conformal field theory is for us. So to a conformal bootstrapper, a conformal field theory is synonymous with this bag of numbers, this discrete set of parameters that we call the CFT data. And these, in turn, completely determine every observable of a conformal field theory, every correlation function. So just to be explicit, a two-point function is entirely determined in terms of the scaling dimensions and spin representations here. The three-point functions are determined in terms of these OPE coefficients, these lambdas here. And in turn, every higher point function can be expanded out in terms of lower point functions recursively using this operator product expansion. So this bag of numbers is the CFT. And this bag of numbers, the CFT data, will be what we want to understand. Yes?
The preliminary question.
Yes.
You said discrete, right?
Discrete.
That limitation of bootstrap?
Sorry, I guess, yes. So yes, that's a very good point. Yes. For example, in something like Liouville theory, you have a continuous spectrum and things like this. I mean discrete just in the sense that, well, yeah, typically we expect there to be some sort of, for Ising CFT, for example, for other CFTs, we expect most things to be discrete. And the only exception that I can think of at the top of my head is Liouville theory, which is a unusual theory, to say the least. But yeah, it's not a limitation of Bootstrap by any means, but just a nice thing to assume to avoid problems later. Great. So I should say this bag of numbers, you can't just pick any old bag of numbers for the CFT data. The CFT data must respect all of the consistency conditions of the correlators. So for example, it must respect all symmetries and selection rules. It must satisfy all global symmetries. And most notably for us here, it must satisfy a certain kind of associativity condition on four-point functions and higher. So here in the example of four-point functions, I have an example of a four-point function here, 1, 2, 3, 4. And you can instead write down 3, 2, 1, 4, which is related to the previous one by some kinematic factor that you can determine ahead of time. And if you then expand this out through an OPE, you get a summation over here and a summation over here of these lambdas, different sets of lambdas, which represent, if you like, projecting over the space of operators. And these conformal blocks, which are known functions that you can compute that have no theory-specific information. And this here? Okay, yes, K is just some kinematic factor that you can determine with like a couple of minutes of, yeah, sorry. Yeah, sure. Change the order of the operators? This correlation function? Yes, yeah, that's okay. Yes, it's a very good question. So, right, so in general, for a correlation function in Euclidean signature, yes, you can, it's automatically time ordered, right? So this sort of a thing doesn't matter. I'm being a little bit, what I'm using this as a shorthand for is we like to assume that everything is in something we call a conformal frame. So we have, say, O1 here, O2 here, which is at location Z, Z bar. We have operator O3 here, which is at 1.
We change the coordinates of the points. That's what you mean?
That's right.
So
that's right.
Earlier,
that's right.
O1 was at 0, and now O3 is at 0. Is that or whatever?
That's exactly
that's
it.
what you mean?
That's exactly it. Yeah,
so there's just some transformation of finding. Thank you.
That's right. So in fact, these are related to each other by just a simple rotation plus some translations, and that's how you can get this kinematic factor. That's all. Yeah, I should specify that when we talk about correlation functions, we typically like to gauge fix away all of the coordinate things as early as possible. So yes, so then the assumption of unitarity also imposes some extra conditions on us. So for example, the deltas that appear, the scaling dimensions, have to be above some minimum unitarity bound. Additionally, these lambdas have to satisfy a certain kind of reality condition. In our context, the reality condition is very simple. These are real. But in more complicated scenarios and higher dimensions, for example, it may not be literally that, but it amounts to that. And so you have a product of real numbers here and a product of real numbers here, plus some known functions summed over in some non-trivial way, and these must be equal to each other. And with a bit of massaging that I'm not going to show you, you can state all of this in terms of a positivity problem that, in other words, you can write all of this in terms of all of this must be greater than or equal to 0. And that is something that you can solve using convex optimization techniques, which is a well-known thing to do with computers. So we can ask the question of what selection of data, delta, L, lambda, are self-consistent in this manner. And that's the program of the conformal bootstrap, to find what sorts of CFT data are even allowed at this level. Great. So the specific CFT that we're going to be targeting here is the Ising CFT, the 3D Ising CFT, and it describes the critical phase transition of the 3D lattice model, 3D Ising lattice model. But for field theorists, it's more familiar as the critical point of phi to the 4th theory, the strong coupling. And the main things I want to point out here are just that there's an operator called sigma, that we call sigma, which corresponds to the magnetization in the Ising lattice model picture, which is odd under a Z2 symmetry that this theory enjoys. So phi goes to minus phi, clearly sigma, which is identified with phi, is odd. And then we have epsilon, which corresponds to phi squared, or the energy density, which is even under Z2. And both of these are scalars. And these are the only relevant scalars in this CFT. There are no others. And this is an assumption that we're going to use. And the notation we'll use is that delta sigma prime is greater than or equal to 3. And what this means is that the next scalar that's odd under Z2 has to have dimension at least 3. Because we're in 3 dimensions, these are now irrelevant deformations to your action. And we want to know all these various correlation functions involving sigma and epsilon, these scalars, which is determined by these CFT data, delta sigma, delta epsilon, lambda, sigma, sigma, epsilon, so on and so forth. And the question is, what does this get us? And it turns out quite a lot. So if you just impose consistency conditions on the 5 correlation functions of scalars, which I've listed here, it turns out famously that you restrict the entire parameter space of delta sigma, delta epsilon, they're quite small here, unfortunately, into some compact island here, plus a peninsula, which will go away. And this little island is exactly where we expect the 3D Ising CFT to live based on Monte Carlo evidence and others. And so this region here is the result of pushing the numerical methods quite hard with just this system. And you can see it gets very, 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 very small. And yes, so there's a numerical truncation involved. This lambda equals 43. You can keep pumping it up as high as you'd like. But the interesting thing about lambda is just that if you have a bound, if it's disallowed for some lower lambda, it will always be disallowed for all lambda above. So it's monotonic in that sense, which is why we like it. And we were able to determine delta sigma, delta epsilon, and these various OPE coefficients to a very high degree of precision, very many decimal places, which is the world record determination. So there's a big happy success story, and everyone is, well, this is a good moment for physics, let's say. Yes? This curve here? Yes. Yeah, great. So the dotted line here corresponds to the bound if you just impose this consistency condition. You just impose sigma, or you forget about epsilon and just look at consistency of the sigma correlator, then you find that you get a bound that looks like this. So all of this is allowed. And it has a sharp corner exactly where we know the 3D Ising CFT to be. And then as you add more correlation functions into it, we were able to close up the space to just get this island. This solid line here is what we call the, if you want, it's the Ising continent or Ising peninsula, if you'd like. And this corresponds to other possible CFT solutions that are consistent with our assumptions. So we're imposing consistency conditions on just the correlation function. We're not imposing any Lagrangian or anything. So any number of CFTs that have a Z2 symmetry can very easily have correlation functions just like this that satisfy all of our assumptions like this. And all of those will be in this region here. So as an example, if you loosen this assumption slightly to 2.8 roughly, the n equals 1 supersymmetric Ising CFT is right about here. And when you loosen the assumption of this, this loosens the bound a bit here, and you're able to find the n equals 1 supersymmetric Ising CFT right there, for example. There's also the Gross-Nevo-Yukawa CFTs involving fermions and Yukawa coupling that are also going to be in this region here. So,
It is possible that that island, that very small island,
no.
there are more than one CFT there.
Absolutely, absolutely, it's possible. We don't have any definitive proof one way or the other. Though I'll show you why in the next slide. Actually, why we feel very strongly that there's only one CFT there. And so if there aren't any more questions on this slide, I can move on. Yeah. Yeah.
Or sigma prime and epsilon prime.
Mm-hmm.
You say something about that. Can you repeat it? Like in the last slide, you said.
Yes, sorry, yes. The assumption is just that what this means is that the next to leading Z2 odd scalar is going to have dimension at least 3. It's going to be irrelevant. And likewise for the Z2 even scalar, the next to leading Z2 even scalar. And so these assumptions are very solid, both because we have theoretical knowledge of it, but also because you can get to the critical point of water with pressure and temperature. And that's just 2 of them. That means there's only sigma and epsilon.
Other operators are given.
That's right. That's right. Everything else is irrelevant. So there was a very nice question asking, how do we know that there's just one CFT inside of this island? And the way we know it is that actually the results don't stop with the island. So what we can do within the island is we can extremize, for example, the central charge. So we can ask for the solution with a minimum central charge that satisfies all of our conditions within this island. And when you look for something that's extremal in this sense, there's a unique solution. So there's a unique solution that comes out of this. And there'll be, in principle, a unique CFT for each and every point in the island. But when you compare all of them with each other and average them together, which is what this big picture is here, you find that they're all very consistent. They're all very consistent with each other. They all have roughly the same spectrum, maybe a little bit moved here and there. And so this plot is plotting spin against dimension, or twist really, so dimension minus spin, for the even sector and the odd sector. And you can find that there's these very strong trajectories here of operators that all have roughly the same twist in both of these plots. And well, these trajectories are stable across the whole island, and that gives us some confidence that, first of all, the CFT is unique. But the existence of these towers of operators is actually predicted by the light cone bootstrap, which is an analytic technique. And with the light cone bootstrap, well, the light cone bootstrap gives us the expectation that these should be there. But then beyond that, people were able to study these more carefully and eventually come up with analytic expressions that actually interpolate all of the data that's shown here. So all of these are individual operators of different spins, but this plot here, these points are the individual twists here for this lowest trajectory over here. And the blue line here is an analytic expression that only comes from delta sigma, delta epsilon, and a few OPE coefficients. And that's able to very nicely match the numerical data just using this analytic method. And I would emphasize that this is an analytic structure that relates all these operators to each other, which is something we didn't know was there before. In fact, it's described as a light ray operator or a detector. And I think this is one of the most exciting things that has come out of the various conformal bootstrap studies. And there's a lot of exciting work being done on this front. I will not be talking about it, but just to say that the numerics gave us these very nice analytic results. Yes, good. So the yes, so everything that we've had is consistent with epsilon expansion results, but it's kind of difficult to get epsilon expansion results to work so well all the way down to d equals 3. You have to do resummations of different kinds, and early on there was a lot of work done to compare the results, but after a certain point it didn't feel fair to compare those results against ours. But yes, actually, I should actually specify this line here was additionally rederived in perturbation theory using the epsilon expansion. So instead of finding, say, the anomalous dimension of a given operator, they found the anomalous twist for an entire, anomalous dimension for this entire tower as a function of spin. This is work done by David Simmons-Duffin, Simon Caron-Huot, Murat Kololu, and friends. It's detectors and weakly coupled field theories. So if you're interested, you can actually directly compute this from epsilon expansion, and it matches this reasonably well when you're taking into account that epsilon is going to be quite big here. Further questions?
Yeah, my question is, you said at some point that the CFT is unique. But of course, the bootstrap doesn't typically unique CFT.
Yep.
You get some region.
Of course. Yeah.
So does that matter for some of these, for some of these unique size calculations that you might actually be looking at a family of CFTs rather than one CFT?
Absolutely. It does matter. I guess these calculations that were done like this, none of these data points are actually the data points that come from a single bootstrap result, let's say. They come from some ensemble average of the whole region. So
Yeah, you don't expect there are any such things. In reality, you expect there's only one CFT.
that's right. Absent supersymmetry or anything, you would expect that there should be just one.
But somehow that's not something you would ever see in the bootstrap, or you might see that.
Yeah, I guess the thing is in the bootstrap, because we are truncating our system in various ways that we are very confident in, and nothing that should be a cause of concern per se. But you'll notice that, for example, it just cuts off here, right? There's no extra operators here, but we fully expect this tower to go all the way to the end. So you can imagine that when you have this truncation here, then missing these operators here, you can fiddle a little bit with these other, the dimensions and OP coefficients of these other things to get some sort of a solution in some finite region, just because you're working at some truncation. That's it. Right. So this is all very nice story, and you might say, oh, well, we've already done it. What do we need to do more? Do we just need to keep raising the derivative order? And you could, but not quite. There's more things for us to understand. So one very specific thing in mind is there's certain operators that we expect to be in the spectrum that we call these double twist directories involving TT, T epsilon, T sigma, that should be present. That should be present in these plots here. It should be there, but they're not. We don't see them, and so we have some intuition that we kind of need to be looking at the T times T OPE itself in order to be able to see these operators, which we haven't been doing before. Another thing is that there's this OPE coefficient, lambda TT epsilon, which controls sort of next to leading order trajectories, being able to do calculations like the analytic ones I described in the previous slide, that have recently been computed using the fuzzy sphere method, as well as the 5-point bootstrap, which is a non-positivity-based bootstrap, so it's not rigorous in the same way. And they were able to get a number that's roughly around 0.9-ish, but it would be nice to have a really sharp insight into this. Additionally, there's the parity odd operators, which the Ising CFT has a parity odd sector, but it's extremely high. The gap is very large. It's like on the order of 10. And that is, we haven't been able to access it in our previous work, and other methods have tried to access it, but also have trouble with it. Then there's data that no one has actually computed. So this 3-point function here, the TTT 3-point function, has these numbers NB and NF, which I'll talk about a little bit more later. But this data is related to the ANAC condition. Yes, these satisfy a positivity relation. That is the ANAC. And then finally, of course, can we push the island to be that much smaller? Can we get even better than the plots that I showed before? So all of this is pointing us towards bootstrapping the Ising system, but with the addition of the stress tensor included. So all of the correlation functions involving the stress tensor, as well as those of the scalars before. Okay. Great. So people have studied the stress tensor or conserved currents in the bootstrap before. So these are some plots from previous studies of the stress tensor system, a pure stress tensor system, and a pure current system, respectively, abelian current. And there's some very interesting results. In particular, it's a little bit hard to see here. This gray line here corresponds to where we expect the Ising CFT to lie. And there's a kink right here, a corner here. So somehow the pure stress tensor system, just the correlation function of TTTT, seems to know where Ising is. But it would be nice to know if that's a real thing or not. I should also mention that people have studied systems of stress tensors before in ABGM theories and n equals 4 superconducting mills, but it's a little bit cheating because you can just work with scalars, and that's in the same supermultiplet as the stress tensor. So, great. So why should we bootstrap the stress tensor? Just some intuition here is that these low twist operators are expected to be very important, and nothing has lower twist than conserved current outside of scalars and things like this. And another thing that's a little bit of a subtle point is that it's not easy to impose the existence or uniqueness of a stress tensor otherwise. So if you do the traditional just scalars bootstrap, you can't enforce that there has to be a stress tensor or there has to be just one stress tensor. And the way to do it is to introduce it as an operator in your correlation function itself. Additionally, another subtle point is that the numerical bootstrap does not enforce locality as strongly as we might like. And it's related to this point, actually. And forcing there to be a stress tensor means that we have a very strong version of locality included in our theory. And finally, sort of a big picture point is that if we can bootstrap stress tensors more effectively, then we can access lots of theories that we never had access to before because we don't have a scalar to access them, for example. So the only operator you're guaranteed to have in any local unitary CFT is a stress tensor. So that's a big picture question. Yeah. That's right. That's right. That's right. So now you might ask, why has no one done this before? Why has no one bootstrapped a stress tensor? I mean, people have, but never mixed with other systems. Sorry, yes. Yeah.
Not generalized species, but other cases, where the stress tensor doesn't appear naturally to a bootstrap without the stress tensor.
No.
Is there any such case known? You can solve the bootstrap without the stress.
Yeah, that's a very good question. So it's not so I should say that in principle, the paper and pencil version of the bootstrap, you should never be able to solve it without the stress tensor. But in practice with the numerics, it is sometimes difficult to distinguish between a stress tensor that's exactly at the unitarity bound, that satisfies all its conservation conditions, and a spin-2 operator that's just a little bit higher in dimension that no longer satisfies conservation conditions like this. So in other words, you would need to, in order to exclude this possibility, you have to put a very large gap in the spin-2 sector. So you need to be able to assume that there's no operators near the stress tensor to force the existence of a stress tensor. But even that can be a little bit flaky because you have, for example, if you have currents, you can easily construct something that ends up looking roughly similar. So it's not that the stress tensor doesn't exist. In the true CFT data, we fully expect it to exist. It's just that numerically, you might be able to get away without actually having a true stress tensor.
And we could think of that as bootstrapping a CFT that's coupled to something else. Maybe it's if you have a CFT which functions in an open system,
that's right. That's right.
These other stress tensor operators are like that.
Exactly. That's.
People often take this field where they imagine other interactions which are much stronger than gravity.
Yes.
You have non-trivial correlation functions.
Yes.
Which are not mediated by the stress tensor.
Yep.
That would actually be like our world. It would, if one could find a CFT like that, it would go some way towards solving the hierarchy. In our world, it is indeed the case that gravity is much deeper than that.
Right.
But if you could really show you get such a CFT in ADS world with the hierarchy, I don't think we know of any such CFT. And I don't know if the bootstrap. I don't thought all the CFT is somehow in the swamp land and work bootstrap.
Right.
Tells us that you cannot really have hierarchy. Maybe
Yeah, I mean, that's so. I guess you're asking. You have a correlation function that's controlled by something other than the stress tensor. You mean, but the thing is, in the true CFT with the full CFT data, every single correlation function whose symmetries allow for there to be an exchange stress tensor will have an exchange stress tensor.
The stress tensor will be controlled by.
Mm-hmm.
Can you generate a hierarchy where other interactions, the other operators are stronger in the central type?
Yes. It's a good question. I think there's some work that has this flavor that by Liam Fitzpatrick and the BU group. They're studying, they're looking at just the O2 CFT, so just the complex version of this, if you'd like. And they go and they study precisely this question of like, relative to the central charge, is the current, for example, the flavor current, is that, how is that central charge related to the stress tensor central charge, specifically with this like weak gravity idea in mind? So that might go along that direction. But, did it? Okay. Okay. Yes, just to say that bootstrapping stress tensors is a very technically challenging thing from a computational perspective and from an analytic perspective, unless you have SUSY. And you get these, in particular, the conformal blocks that go into your consistency conditions. You have to compute them. They're very hard to compute. There's, because of the spin of the stress tensor, there's a lot of invariant tensors that all need to be handled. And the stress tensor obeys conservation, so you need to look at invariant tensors that also are conserved. And if you have other operators other than the stress tensor, you have to recompute the blocks every single time you do a single point of your bootstrap. So it's very, very painful to do. On top of this, the system of equations is massive, and computers might, getting a computer to be able to handle all of that is an engineering challenge in and of itself. And essentially, this is a new scaling paradigm for the numerical bootstrap. Like you need to be able to handle this level of complexity of blocks and crossing equations and put it all into a computer and hope that it all works. I should say that this engineering challenge is not unique to the stress tensor. So if you want to compute superconformal blocks, for example, it's a very similar story to this. So the same engineering challenge that we solved for the stress tensors is also useful now for working with superconformal blocks directly. And the reason why we feel that we're able to even get away with all of this, face this engineering challenge, is that there's been a tremendous amount of technical work that's been done to build up the numerics in the bootstrap. It's a little bit hard to see, but this is some recent results of ours studying fermionic CFTs. And there's a very nice review by Slava Richkov and Ning Su here, if you're interested to see what the progress has been like. So with that, yes, I know having an outline 30 minutes into a talk is a scary thing to see, but I should say the setup will be quite quick. Implementation is technical stuff that may or may not be interesting, and this is optional stuff. I'll talk a little bit about the pure stress tensor bootstrap results that we've had recently, but the main thing will, of course, will be the full bootstrap system and the results that come from that. So on to setup, the way that you do a bootstrap is just write down some paper and pencil representation theory results. So given a correlation function, you can always decompose it into invariant tensors that satisfy conformal and flavor symmetries, as well as conservation and things like this. Additionally, those invariant tensors, or the degrees of freedom associated with the invariant tensors, have to satisfy crossing relations, which is this permutation ordering of these operators here. And any of these 4-point functions can be expanded out in terms of 3-point functions, or conformal blocks, in other words. This is the conformal block expansion. I'm just saying it's a very trivial point, really. It's just that you can, if you have a correlation function that preserves your symmetry, you can decompose it into invariant tensors associated with irreducible representation, let's say. So it's basically saying if I have a symmetric tensor, I can write it as a symmetric traceless tensor in the trace. That's all. But that is really the main ingredient in the entire conformal bootstrap story. So the main new thing that comes from studying stress tensors is that you have to make sure that everything is conserved. This is really a sort of a technical calculation that's not very interesting, so I'm just going to skip over it. Just suffice it to say that there's a lot of subtleties, and it's very, very important to have exactly the correct enumeration of degrees of freedom in all your correlation functions by doing this. So in total, we have all of these are these are the paper and pencil results that we need to be able to do a numerical bootstrap of the system. So here I have all of the different operators that appear in the different OPEs. So the sigma, sigma, epsilon, epsilon, and sigma, epsilon, all of these were the same things from before, from just the sigma, epsilon bootstrap. And all of these are now totally new to this study. And something to note is that we have access to parity odd structures. So that's what this 1 minus notation means, is that there's a parity odd structure. Additionally, we have access to spin odd Z2 even operators for the first time. So there's, yes.
Why did including the stress tensor force you to parity odds sectors?
Yes, very good. So you can, with the stress tensor included, then you can put an epsilon tensor on it, contract it with an epsilon tensor, and that'll give you some parity odd operator. That's the easiest way to think about it. The scalars have no external indices, so you can't apply some you can't apply epsilon tensor to that. Sorry. Well, it's not a. Yep. Yep. Yeah, it was, for example, you can write down just to write down a sort of trivial one. So you have sigma here, and then you have. Oh, sorry. Is there a way to? Okay, sorry. So you have sigma times t mu nu epsilon mu nu lambda, for example. Sorry. Yeah. You're right. No. I made silly mistake on my part. So these are contracted here, let's say. So this is left free, and then these are the remaining things. And for example, so that's not a primary anymore. It's a total derivative. Uh-huh. Yeah. Mm-hmm. Right. Yeah, but then okay, just to say it somewhat, it will, in the end it'll vanish because why do I have what's a nice argument for this? Some scalar. Yeah, but you're asking for if you can write down some 3-point function. You're asking if you can write down some 3-point function like that. And then epsilon. Yeah. Yeah. I'll be honest and say I'm not used to thinking in terms of constructing it out from this. It's much more obvious from the perspective of if you look at what invariant tensors are allowed under this, it's pretty clear that there's none that are parity odd in the basis that we have. I mean, one way to put it is.
In terms of the icing, 3D icing, right?
So is this icing? So we have to icing. Okay. So I was thinking more generally. I was not thinking in terms of only this. I was thinking. Okay. So here.
Is this sigma epsilon and stress tensor, right?
Okay. So you're saying here you could only think in terms of sigma epsilon stress tensor. Okay.
Yeah.
My why can't I take d mu sigma, d mu sigma?
Right.
Acting some derivatives with sigma, I create an operator of this kind.
Right. So the closest thing you can.
That's not primary.
Well,
Derivative of sigma itself is not primary.
It's not a primary.
No.
It's a descendant. And then I multiply it with another descendant. So
Yeah.
I was only trying to understand in the OP, all these operators, this is also an operator.
Yeah.
Why did you get, sorry, my question is very simple actually, maybe I don't want to give you, why did you less than the force you into parity or structure that you could have forgotten about?
Yeah. So I guess the subtlety is that you can.
The operator was already in the spectrum. It's not a primary, it's in the spectrum.
No.
Why did they include the stress tensor?
Yeah. No. All the operators, relevant or irrelevant, are all part of it. No. Maybe the way to put it, the way I would put it is that. Yeah. Yeah, that. What? Okay, I don't know what that was. No, the thing, maybe, okay, I should say, by the way, if you just have g mu phi and epsilon mu lambda, this is not suddenly a parity odd operator, right? This is still the same thing as this, just with some reindexed things. So what you're suggesting, writing down d mu phi, exactly. Yeah. So in the same way, if you now have That's right. So this operator I wrote down is also bad in this way. Yes, you're right. So it's maybe the best way to put it is that you can take a curl of this. So you can take the curl of this, of t, and that will now be parity odd. And you can't take a curl of a sigma. That's the. Yes. So these are parity odd structures here. So anything involving the stress tensor here, there's a possibility of there being parity odd spacetime structures that were not there before. And I think the best way that I can put it is just everything that you can write down as a descendant, whose product with something else might well be a primary, ultimately amounts to some differential operators that you apply to whatever operator you're in, and you can apply a curl to a spinning operator, but you can't apply a curl to anything related to sigma. So the sigma is what the curl is what gives you the anti-symmetrization of indices is what gives you your parity odd, and you can't anti-symmetrize any of the indices that come from not easily, but you can't anti-symmetrize any indices that you could get from this kind of a 3-point function.
So your definition of parity odd is what about epsilon active? Yeah.
So
what sigma? What about sigma? So what is the definition of parity odd?
Definition of parity odd is very good. I mean, it's the standard it's like a reflection across one of your spatial dimensions, let's say. So sigma is parity even. It's Z2 odd. There's a global flavor symmetry called Z2. It's a little bit confusing, but sigma is parity even itself. Exactly. That's right. Spatial parity.
You have to have epsilon.
Exactly. That's right. Yes, that's right. And there needs to be an epsilon tensor relating to different operators non-trivially, and that's not, or relating a derivative with a different index non-trivially, and that can't happen if you have only scalars. It can only happen.
In this case, so how is the epsilon tensor acting?
The epsilon. Yes. Yes. No. So the way that we do it is we enumerate the invariant tensors to start with, and we're not actually working directly with contracting any indices anymore. Ultimately, we're writing down some conformally invariant tensors that then get fed into a software that gives us conformal blocks. And depending on what the invariant tensor is, it'll either be parity even or parity odd. That's,
sigma of minus x, sigma of x, probably if you run the odd structure there in that OP.
yeah.
And probably for TU, that's not the case. Because, you know, there are some polar reflection positivity also knows some polarity.
I think of reflection positivity as being unrelated to this, but now on thinking about it now, it could very well be, yeah. Mm-hmm.
How do you write parity or structure?
Yeah, you can't. Yeah. Yeah. Yeah.
But with TMU, we could write what? For instance, you could write, with TMU also you might have thought.
Yeah.
What parity or correlator would you write if you had T? This is what's confusing me.
Yeah. Yes.
One index to the T and one index to some derivative.
Yes. Yes. That's right. That's right. So the first parity odd operator you can write down in Ising, by the way, is something quite horrible. It's like D, D, D. So it's phi, D, 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 phi, D, 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 phi.
You're probably get these two different 3-point structures.
That's right.
One of which have to do with the plus, 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 and the minus, 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 and then
Exactly.
Right.
Right.
The question of whether the other structure appears or not is so that's what you're saying.
That's
so for the 3-point function of 3 p's, there are two possible structures. There is
yeah.
a 3-point function of 3 sigmas.
That's right. That's right. Exactly. That's right.
That there is this additional structure which maybe comes because there's one of these other.
But it's also a structure that is parity. So if you have TTT, there are two structures that are parity even and one that's parity odd. That's right. Right. That's right. Yeah. That's right. That's right. We have our own in-house way of writing things as opposed to helicity notation, but that's essentially exactly the point. So I should say now that we have 53 crossing equations now that come out of all of this, as opposed to the 5 that we had before. As we've discussed, there's a bunch of new sectors included. I wanted to just briefly mention the assumptions that we put into our work. So these two assumptions up here are the same assumptions that are in the original scalars only Ising bootstrap. So the sigma prime and epsilon prime are irrelevant. And our justification is that we know the value from this. Additionally, we assume that the parity odd Z2 even, so the flavor symmetry singlet, but parity odd scalar should be at least 3. And this is actually a very conservative condition assumption because we know it should be around at least 10 through other means. And finally, we have a gap above the stress tensor, so the singlet parity even spin 2 dimension of at least 4, and we know that that should be at least 5.5. And finally, we impose a small twist gap, but just for every other sector that's not included, we just say that the scaling dimension has to be just a little bit more than a twist of 1. And this is, again, pretty conservative because we know that it should be around 1.022. Great. So I wanted to highlight actually specifically the TTT 3-point function. So as we said, there are two parity even structures that appear. And it turns out a convenient basis for these parity even structures is this one, where this invariant tensor here is exactly the invariant tensor that appears in a free scalar theory. And likewise for the free fermion theory here. And the reason this is particularly convenient is that the ANAC requires that these two coefficients here be positive, or at least non-negative. And in particular, for any interacting theory, these should be strictly positive. The only thing that's allowed to saturate this being 0 are free theories. And these are related to the central charge through this relation here. So this is some standard central charge for the free boson, free scalar, free fermion. And that's why we can write things in terms of NB and NF, which is related to CT in this way. Now, the interesting thing is that no one has actually computed these NB and NF in any capacity beyond leading order that I'm aware of in 3 dimensions. But we're sort of obliged to study this because we need to include this OPE channel in our theory. So this is a little bit interesting because this NF, in some sense, you can say is like how fermionic is the Ising CFT if you're being a little bit silly, but. That's right. So I should have said earlier, we're assuming that there's that the whole theory is parity invariant. So we're assuming that there's no parity breaking things going on. That's why we were able to discriminate tensor structures into parity even and parity odd. Yes, if you included parity breaking terms, there'd be a third term out here. So. Yes. Yes. To leading order, and yeah. Yes. So yes. So in particular, yeah. Just yeah. If in the Chern-Simons case, you have some parameter here that's some theta, which is a function of n, b, and nf. Let's say. Say this is this axis, and it has to be within this range. Then there's an additional parity breaking parameter, let's say y parity breaking, something like this. There's a circle, and every theory has to be within this circle. And as a function of lambda in these large N Chern-Simons theories, you go around the circle. That's the picture. So here we're taking just a slice like that. Sorry? Uh-huh. Uh-huh.
So there are many computations where holographically 3-point functions of gravitons.
Uh-huh.
You can add different aspects, so you take the Einstein gravity term, you can add higher direction. There are different combinations of energy.
Yes.
And so it's not true that no one has computed energy and F.
Well, I wasn't. Okay. Okay.
But that dual theory will satisfy bootstrap.
Yeah. Okay.
Oh,
okay. So this is the next to leading order, or is it just to leading order? In n, 1 over n, let's say.
Yeah, you're right. These computations are the computations are probably leading order.
Yeah.
But you don't have to be on the extreme thing. You can be in the middle. And I guess you could ask the 1 over n squared correction.
So.
Those are probably
also
being computed.
Okay. I wasn't aware of this, so I'm very happy to hear it. So if maybe afterwards we can chat. Yes. Yeah. Yeah.
I'm not sure.
Okay. Okay. So I'll ask you for some citations afterwards. But.
Yeah, I mean, Madison and also
yeah. Yep. Yep. Mm-hmm.
We also did difference of B, for instance.
Yes. 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 Yeah. Okay. Great. So now onto the technical implementation, the coding stuff, what we did. So as I say, we took crossing equations and we turned it into a positivity problem, which is turned into an optimization problem for a computer using our software SDPB. And we can then see if our assumptions are disallowed or not yet disallowed. And for our assumptions, we choose values for this 6-dimensional parameter space. You'll notice that it looks like there's 7, but these OPE coefficients are actually only related. They're in projective space. They're only defined up to some overall scaling. It's a 6-dimensional parameter space. We plunk down some assumption, and then we ask the computer to tell us whether it's disallowed or not yet. And we use various search routines to get through this gigantic parameter space, in particular this cutting surface algorithm for the OP coefficients and a Delaunay triangulated like mesh search for the scaling dimensions, which both were described in this paper before. Then once we have those assumptions, we need to compute all of our crossing equations and turn it into a program for a computer. And we have this gigantic stack of at this point, very sophisticated code to compute conformal blocks, to combine them into conserved blocks, to compute the whole positivity problem using the crossing relations, and then to convert it into something a computer can understand, and then do it. And every single step along this way, by the way, was significantly improved in the process of this work, because this stress tensor bootstrap is very technically difficult, and we had to basically everything from touch up to rewrite every single thing along this stack. So that's all. And you can find our code on this website here, in this GitLab repository. There's about 5,000 lines of project-specific code, so to set up like all of this bootstrap things, and then another 7,000 lines of specific runs, like searching in specific parameter spaces with specific numerical parameters, things like this. Even though this is a lot of code, which it is a lot, it doesn't take that much to modify it to something new. So, for example, adding a different scalar, removing a scalar, putting a current instead of a stress tensor, you only need on the order of 100 lines of new code to get something else running. I know because I did it. I took our stress tensor code and I converted it into currents code, and I was able to do it in like an afternoon. So this is a very extensible and flexible piece of code that we're hoping to use for lots more things. Our ultimate computations took on the order of 10 million CPU hours. This may not mean anything to you, but this is a hefty amount of CPU time, but not so hefty that a typical computational physicist would be very impressed. This is a kind of a minor amount of computational work. So now onto the results. So you might ask, will any of this work, will all this work, and putting a stress tensor into it, is that worth it in any way? And it turns out that yes, it is. So this blue plot here, this blue circle here, is the old island that I showed you that was super tiny, that was a world record from several years ago. And now we've been able to shrink it all the way down to this very small island here, this little red one here, which is about 40 to 50 times smaller than the previous one. And I should say this is at the same derivative order here. So this system is now a strict superset of this system. So the same derivative order gets us a much, much, much tighter bound. Now to give you a sense of how well things are converging, what happens if we keep pumping up the lambda, the numerical order. So this is the same. So in this plot are the red and green circles here. We've done an affine transformation on them to make them map to spheres. And you can see that as we go from one step in derivative order to the next, it shrinks by over a factor of 2 in each of the different dimensions. So it's still going very well, and there's a lot of headroom basically left. Now here are our actual results of the different CFT data. So we have effectively 2 more digits on the delta sigma and delta epsilon relative to what we had before, as well as several more digits on the various OPE coefficients and the central charge. Something new here is that we have access to this lambda TT epsilon that I mentioned earlier. So we're able to determine it to a significant number of digits, which is consistent with the 5-point bootstrap result from before, but has some tension with the fuzzy sphere results that people got for that. And then finally, we have these NB and NF, which we discussed earlier. And this is the first ever determination of these NB, NF for the 3D Ising CFT. So just to comment on that briefly, if you now take NF over CT, you can get a percentage, and you can find that the Ising CFT is 3D Ising CFT is 1.38336 percent fermionic, which is a bit funny. But again, as of writing this presentation, I wasn't aware of any other results that were remotely similar to this. So it's very hard to get a sense of, is this big, is this small, is this medium? Like, I would really like to know that. That would be something that would be very interesting. In particular, because I'd like to track this across other families of CFTs, and in particular in gauge theories. So there's several gauge theories, lots of gauge theories in 3D that are expected to have these bosonization, fermionization dualities. And it would be nice to be able to see that from the bootstrap perspective, because the bootstrap shouldn't care whether you think about it as a gauge theory with fermions or a non-gauge theory with scalars. And in particular, these same parameters, there's analogous parameters, including f mu nu and a current J. So I think this is an interesting direction to explore. Yeah.
The fact that you have some non-zero NF, does that mean that there are fermionic operators at a higher operators?
I would say no, simply because the selection rules make it like it's not clear to me how you would end up with. Not obvious to me what this literally means. There's a fermion floating around. Yes, it could be. I guess I would caution against interpreting this a little bit too literally. I think it's sort of the fact that we call this NB and NF is just by relation to the free theory, but this is a fully interacting CFT, and it doesn't know what the free theory is. It doesn't think of itself as being from a perturbative expansion from a free theory, and this. Yeah, it's. I would like to think about it and try to understand what this means. I mean, one way to maybe think about it is this is maybe telling you that if you tried to get the Ising CFT from a free fermion theory, like start with some free fermions, add some interaction, and then flow down to the 3D Ising CFT somehow, that it would be a very long and circuitous route, because this OP coefficient would change quite a lot. Whereas if you're coming from the free scalar theory, it's a very simple flow. You just one and done. Yes. Yes. Right. Also, we have some bounds on the parity odd scalar in the Ising CFT. So these are the first like sharp bounds, if you'd like, on the 3D the odd operators in 3D Ising. And we can say that, so this plot's a little bit confusing, but this axis here is the dimension of the leading parity odd scalar. And this is the gap to the next to leading one. So in other words, we're playing with how isolated is this leading parity odd scalar. And it turns out that the lower bound on the dimension is pretty inconsistent, and it's hard to make any claims. But the upper bound for sure seems to be pretty solid and consistent at 10.92, which is quite a bit away from the fuzzy sphere estimates. So either this is going to converge way down that way, or the fuzzy sphere estimate is incorrect in some significant way. Now I'll give you a numerological riddle, just for fun. So in 2019, Ning Su guessed the following analytic forms for delta sigma in the Ising CFT, as well as the n=1 super Ising CFT. And these agreed to 5 decimal places, which is the number of decimal places we had determined at that point. Also, we know that the n=2 value directly. So the question is, how well did this numerological guess go? A guess that had no physical reason to be correct. And it turns out that it did very well with 2 more digits added. It's still correct. It's still correct with now up to 7 digits of agreement. I should say the way that Ning guessed this number, or this expression in terms of gamma functions and all that, he went to an inverse symbolic lookup table and looked for things that looked reasonable and seemed to match each other across the non-supersymmetric Ising CFT and the n equals 1 supersymmetric Ising CFT. So who knows? Maybe there's something there, maybe there isn't, just for fun. I spent about an afternoon trying to massage this into a form that could, connect this with this, but no dice. It wasn't easy. I should also say we have some unpublished results hot off the presses, or not yet off the presses. And the central value of the 0.6 here is a little bit below 0.8. It seems to continue to be going below to 0.4. So maybe this is the end of the road for this guess. Yes. Yes.
Can you comment whether it is something special that the dimension of whether the dimension is rational or irrational?
You mean for these It could be.
Well, this is rational, right? Yeah.
Well, these are obviously irrational.
The last thing you have written, which is supposedly known exactly, is rational.
Yeah.
Something special.
No, it's just protected by the superpotential. You have a superpotential that looks like some cubic term basically, and that forces you into having this. So it's not anything particularly. Sure. Yes. So in fact, people have numerically studied this thing, and they found it. I mean, we don't expect these to be rational, if that's what you're asking. Like, these seem very crazy. It's hard to imagine what they could possibly be.
But if this is really true, then this means that the 3D Ising model is solved.
Yes, that would be the implication. But
This is the unpublished result.
yeah.
So this 13 means what? What the error is?
It's the error in the last 2 digits. So the 1.3 here means that this is 0.4 plus or minus 1.3. So 0.6 plus or minus 2.4.
That's still consistent with your with the guess, right?
Yes, but I guess the central value seems to be drifting away from the 0.8.
Central value, but 13 is the error.
Yeah, it's still consistent. It's still absolutely consistent. That's right. It's remarkable that it continues to be consistent even after all of this. Yes, indeed. And just to say this, I showed these plots of extracting the spectrum of like all the operators using this plot that showed all these trajectories. So we have some very preliminary stuff of extracting these this data. So this is very messy data that you shouldn't trust really. But there's one thing I want to point out. This straight line here is totally new. And this straight line is precisely this T sigma trajectory that we were unable to find before. Now we're able to find it. And relatedly, this thing here is another T sigma trajectory, but this time it's parity odd. So it's so these seem to be appearing. So now we actually have things to work with. So now we're working on analyzing the data, but we don't have anything to show for that yet. And now, okay, the only thing that's left is this optional stuff of the pure stress tensor things. So is it 10? Okay, great. So now after I've shown you all of these Ising specific things, now let's step back and look at just the pure stress tensor correlation function. So, in other words, I remove sigma, I remove epsilon, I remove any knowledge of a Z2 symmetry at all. And now we can ask ourselves some questions about this theory. So this plot here is a plot showing the gap to the leading even scalar, parity even scalar, and the gap to the leading parity odd scalar. Okay. So every 3D local unitary CFT that is parity preserving should be on this plot somewhere. And the first thing to remark, this is not a new result, but this is a compact region. This is a compact region. So every CFT has to have some scalars that are below a certain threshold in 3D. Now, the thing that's quite mysterious, so the thing that we've done anew is that we pushed the numerical order much higher now that we have the technology for it. And the thing that's very mysterious is if I overlay the dimension of the Ising epsilon on this, there seems to be a structure right here, a turning point here that corresponds very nicely with the Ising case. And this is now zooming in as an inset, just at the highest order. And you can see that it's pretty close. It's pretty close, like if you see the scale of the axes. And this is a bit weird, right? Because I'm asking if I have a 4-point function of stress tensors, what sorts of solutions are possible with that? And somehow it seems to know that Ising is there. It seems to be very close to knowing that Ising is there, which is weird and mysterious. Somehow it seems to correspond, it has this structure here, this kink, that corresponds very nicely to the location of the Ising CFT without, sorry, the x-axis here is the dimension of the leading parity even singlet scalar. So in Ising it's epsilon, but it just could be anything for any theory. I'm not specifying anything. Dimension, that's right. In holographic theory, it should be quite large, I would imagine. Yeah, no, or not. I shouldn't say large. I don't have a very good intuition for the leading order stuff, or the leading scalars. Yeah. Yeah. So that should. Yeah. So if you have pure gravity, that should correspond to this solution up here. So this is this thing here that I call MFT. This is a theory of purely stress tensors. So there's nothing else in the theory. There's only stress tensors. That's this solution over here. And it corresponds to a very large gap in the even scalar and a medium-sized gap in the odd sector. Yeah, should be a pure stress tensor theory in the boundary, yes?
A lot of the theories have the property that you put the other fields, the 4-point function, the leading order 4-point function doesn't care about the answer to that. Or maybe,
sure.
Because you see, yeah, so if you just say external gravitons, then other fields can contribute through loops. But the three-level exchange is just gravitons.
That's right.
So, if you're just computing the leading order at large central charge, leading order.
Yeah.
It should all be there.
It should all be here, right? I mean, yeah, if you go to the large central charge limit, you should all basically going to here.
There is such a thing as a pure gravity theory. CFT, you believe such a thing exists?
There's a delta, right? You can't do pure gravity.
Huh? Sorry, what?
There is a, that still has a delta C.
Delta, yeah. So this. Yes, yes, but that corresponds to T mu nu. And yes, and then this one here, the dimension 7 one here, corresponds to epsilon nu lambda T mu rho D something, D nu T lambda sigma, like this. The fact that it's sort of stretching the definition of what a theory is. So this is a very weird theory, which is why we call it the mean field theory. It corresponds to only stress tensors, but with the weirdness that the stress tensor is decoupled from itself. So the stress tensor does not appear in the stress tensor OPE. Is this 0?
If you have good gravity radius, right? That you can use it to define a boundary here. You just have the bootstrap.
So not because presumably at loop level and so on, you're running into trouble. You should see that you need like.
Because of the IUV data.
Yeah. So you shouldn't. I mean, this is a much stronger state. At 3 level, you can work with. They seem to be saying that you can really define something which will work.
I would say it's more. I would say this is as much as anything like a numerical quirk as well, because we work with unit normalized stress tensors. So what that means is that the central charge goes to infinity limit. It means that the OPE coefficient with the stress tensor goes to 0. So it's a little bit of a pathological solution. I wouldn't take it too seriously. Yes, yeah, that's right.
For this, your important central charge is
which one? This one here? Infinity.
It's somehow a theory of pure gravity in the bulk, but has only the stress tensor. and doesn't have any. It's not doesn't have an Einstein Hilbert action because it doesn't have a 3 point.
Yeah, it's you should think of it in the same. This is the same thing as a generalized free theory. This is another kind of generalized free theory. Yeah.
Wait, are you saying it's factorized? Like 4-point function factorized is a 2-point function?
No, that's a good question. Yeah, you're right. It's not. It's a mean field theory. It's not. It's even if it's. Yeah.
It's a 4-point function factor. It's a trivial. That's the
Yeah.
first.
Yes. So it must be. Yeah. Sorry. So. Yeah. 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 You can tell that we haven't lost that much sleep about this theory. I think it is the case that the 4-point function just factorizes into 2-point functions. So. Yeah.
Just take 2 areas.
That's complete.
Yeah.
How do you get the parity on epsilons? It's just factorized.
No, there's no parity on because I think
No. There is a parity on scalar. You can build one. So it's a very silly one, but.
But TT, double-trace TT, not scale to all of that.
So the 4-point function is not factorized.
Looks like because I can't see how you get it.
No, this is your parity on leading scalar. Yeah.
The question is the 4-point function a product of 2-point functions or?
No, I guess I can't see.
And that theory is a trivial theory.
No.
That certainly exists.
No, yeah. No, in fact, yeah, this guy here should have a non-trivial OPE coefficient with the t times t. So. Yeah.
It's like non-trivial theory has no 3-point parameters capturing.
Non-trivial 4-point function. What do you mean non-trivial? It's not product of 2 points.
Well, just that it has this exchanged operator with the non-zero OPE coefficient. It has to be. This has to exist because otherwise this gap assumption wouldn't matter. Right. So the gap assumption mattering means that this thing's contribution to the conformal block expansion is important. So I worry about, I think a lot of intuitions about. Yep.
It can be non-zero, right?
Yes.
The double trace operator does contribute in generalized field.
Yes.
Because when you take OX1, OX2, you get
That's right.
all positive.
That's right.
You
Yep.
don't just get
Yeah.
double trace.
Yeah. So.
But that's not inconsistent with the fact that the 4-point function is still factorized.
Yeah.
You just get 3 terms in that factorization.
Yes.
You compare them up to the
Yes, that's right.
the
Yes.
double trace.
Yes, that's it. That's it. Yeah. It's completely trivial. Yes.
Do you get a parity or
This I don't know. But
This will always be there.
That's this. That's this. Oh, yeah.
Yeah.
Um,
If you say it's factorized, just do all permutations of pairs of P's.
you might get the parity or the 3-point. I don't know. But it's not impossible that theory is factorized.
Yeah.
That theory certainly exists.
Yeah.
There
Yeah.
might be other theories I'm trying to understand it.
See?
That's called MFT is actually that theory or it's
I should emphasize one other thing just again is that we're working with the unit normalized stress tensor. Because certain OPE coefficients may not, the numerical value of the OPE coefficient of this, with the unit normalized stress tensor, this goes to 0. And this doesn't go to 0 if you don't do this normalization, for example. Yeah. No.
So TT 2-point function is finite, right?
Yes, it's unit normalized.
I suspect the theory of
Yeah.
I find it hard to see that there would be a
It's
trivial 4-point function like that.
exactly. We think of it as being just a pathological thing that we don't want to. Pathological just in the sense that there's not any interesting physics. Yeah.
Yeah. Take the limit for the coupling goes to 0, the radius goes to 0.
Yeah, or maybe just, yeah.
Yes.
That is
Yes. Right. Yeah. Let me quickly jump to the last few. Yes. Okay.
Areas that have only stress tensors.
Yes.
There is no such thing.
No. No. It seems implausible.
But in the opposite case, you can construct something in the one where it's right on gravity.
Yes, you may be able to write it unperturbatively, yes, but whether it appears. Yeah. Yes. Okay. Very good.
That would be the state. Your gravity is not consistent.
Mm-hmm.
You have to include some strict chaotic excitations.
Yes. Absolutely. Well, maybe the thing to say is that if you just look at this this plot here again, there's no. So I have not shown you this data here, but if you impose there's a finite central charge, then this immediately becomes disallowed.
Yeah.
Yes. It means that this bound here moves in, and immediately this is no longer allowed for any finite central charge. So if you force there to be a finite central charge, which you can, immediately the MFT becomes disallowed. And that one way to, well, the only theory that can have only stress tensors is this MFT. So if it's immediately disallowed with some non-zero central charge, that feels to me some sort of a statement along the lines of what you're asking.
This full, it's not slightly solid line like infinite central term.
No, that's a good question. So it's just this pocket. Yes, and this is the ON vector model. It's a very good question. So this is the large N limit of the ON vector models. So the Ising CFT might be here, and then we have this archipelago all the way down to here. And from this point, it jumps to there, because once you get to N goes to infinity, it decouple things like this. I wanted to show you a couple of more interesting plots. So just to finish it off. So now I asked, what happens if you take the leading scalar's OPE coefficient and maximize it as a function of the leading even scalar's dimension, as well as the next to leading scalar and the next to leading pseudo scalar dimension. And the thing that's so this here corresponds to a slice right here, right? We're taking a slice right here. I'm asking now for each point along that, what is the maximum OPE coefficient here that I can have? And you get some very interesting results. Immediately you get a kink here, like a sharp feature here, which corresponds to the free scalar theory that you can compute and matches exactly. Then there's another kink here, which again corresponds to Ising. So there's a second kink feature that seems to correspond to the Ising dimension. And in fact, with our full mixed system, we find that this turns into just a little island there, which is nice. And then there's a mysterious structure here that we don't know. And it's a little bit hard to see on this plot, but now this is what happens as you change the next to leading even scalar's dimension. So now the z-axis, so coming out of the page, the color is the OPE coefficient. And you can see that there's maybe you can't see, but there's a sharp kink here corresponding to where Ising is. There's a sharp feature here corresponding to the free scalar. And then a swooping line up to here leading to this question mark theory that we don't know. So that led me to think, what happens if I loosen the assumptions further? So go back to the whole big plot and ask across the entire plot, what happens if I maximize this scalar's OPE coefficient? And you get a lot of structure that's quite hard to see. So now let me, I took a discrete Laplacian here just to highlight where there's a turnaround point. And there are these very sharp features, one that corresponds to the free fermion, one that corresponds to the complex free fermion, and it's a little bit hard to see again, but there's this large feature here, large feature here, large feature here. Again, this is a plot of just the OPE coefficients, the upper bounds on OPE coefficients as I change the dimensions of various leading scalars. and with no other assumptions. So every CFT, 3D local unitary CFT should be here. And so I zoomed in a bit. This is less of good of a plot, but the next one is my favorite plot. Here we go. So this is zooming in on this region where you have a parity even scalar between dimension 3 and 4.5, and a parity odd scalar between 2 and 7. And you see this huge, very, very striking feature that seems to be going along this line and has all of these extra stuff coming out of it. And this is essentially a much more complex kink in the same spirit as the Ising kinks that we've been finding. But this time I don't know what these are. I don't know what these could be. And these dimensions are basically inconsistent with any kind of a theory that is not a gauge theory somehow. The only thing that I can think of that appears up here is something like QCD3 in some way or another. I don't know, but this is a mysterious feature, and I wanted to show you all with the minute that I had left. And just to emphasize as well that you can do this again for other scalars. So just with the pure stress tensor system, now the odd scalar, you get more structures just like this in other parts of parameter space, this time highlighting different families of theories. And so that's all very exciting. And this is something I want to explore a bit more. With just a pure stress tensor, what CFTs can there be that we may not have even dreamed of before? Maybe we have dreamed of it, but we never thought we could access it directly. So with that, let me conclude and say that the numerics have plenty of headroom left for the 3D Ising bootstrap, and we've pushed the state-of-the-art another few decimal places, as well as determined a large number of further CFT data. We're analyzing the extremal spectrum right now, and even just the pure stress tensor system seems to have lots of things to say about the space of CFTs that it would be very nice to explore. I guess the question is, why are we finding such structures? Why are we finding like a bootstrapahedron kind of feature when we're studying just a pure stress tensor system? And can we further refine this into islands, for example? And then going back to this 3-point function, the TTT 3-point function, what more can we do? And it would be very nice to get some further results in those directions. And finally, can we go to other systems of conserved currents and D greater than 3? So I'll say that we've already started some work on studying non-abelian currents in 4 dimensions. So we have the code basically set. We're in the process of doing the paper and pencil work, but maybe the target would be to see if we can get adjoint QCD4. But we'll see. But there's plenty of work to do, and I think it's a very exciting set of things to do. So thank you all for your attention. And
please go on.
Of these new features that you were writing in the previous slide.
Yes.
Could they correspond to some supersymmetric versions of these points that you have marked?
Very, very good question. Very good question. That's actually something I was thinking about. So the answer is possibly yes. So this 5 here corresponds to, if you have an R symmetry of 04, which is what you have for n equals 4 in 3 dimensions, then you have access. You now have a parity odd operator that's dimension 5. So that could very well be something like that. Though I should say that supersymmetric theories, as far as I understand, should also have this NF and NB should be constrained to just be equal to each other. And if that's the case, this is now a plot showing this very strong feature where we're scanning across different ratios of this NB and NF at all these different points while doing the same bounds. You can see that the peak seems to move in theta in this ratio, depending on where you are along the structure. So it's unlikely that all of them are supersymmetric, but maybe there's something there that's supersymmetric.
Thanks.
Are there any further questions?
Yeah, I have a general question about what one can do with the holography.
Yeah.
Is there a sense in which you can actually work with large finite central charge and try and ask what kind of structures you can get in the T. It
Yeah.
would be pretty interesting, right? Because
Yeah.
that's the kind of question of what kind of four-point gravitons catching up with people have been studying in other contexts.
Yeah.
Okay. Gravitons catching.
Yeah, it's a very good question. I should say that like yeah, I guess the comment I'll make is from the numerical control bootstrap side of things. When people have studied large N type things or large central charge type things, the power of the method starts to break down a little bit for the simple reason that you start getting hierarchies, OP coefficients, let's say, or things start becoming a little bit more trivial. So I have a little bit of reservation with taking that particular limit because it amounts to the stress tensor being very weakly coupled to itself and probably like in the same large N neighborhood. Things tend to work well when the central charge is very low. The smallest central charges are where we have the best results so far. That doesn't mean that it can't change. Yeah. Yes, that's right. That's right. Yeah. Yeah. Yeah.
Go to higher order, like you ask what are the constraints given on the N square.
Yes.
Given the 3-point function 1 over N.
Yeah.
Might be interesting.
Yes. Yeah, absolutely.
You're saying it's not possible.
It's not that it's not possible. It's just that a lot of numerical bootstrap things, like there's as much art as science in it. And one thing that I've noticed is just that large N type studies, like studies that are comfortable in the perturbative limit or comfortable in a holographic limit, tend to be less comfortable for the numerics. Like you don't get as nice or sharp results. Just to give a very simple example, there was a study of non-abelian currents in 3D where they took N, so it's ON current or something, and they took it N to be equal to 100. That's a huge central charge, but still finite. And they got results, and I think, they're able to get like some sharp-ish bounds, but they're not the most interesting, and they weren't the most converged, and it didn't necessarily tell you anything completely new. I think that's my word of caution, is just that, yeah. Yes.
And then there are loop corrections that have UV divergence, which you can't actually answer from the model.
Yes. Yeah.
Is there something you could say to actually control them from the bootstrap? Like that would be
No.
extremely interesting.
I see. Yeah.
Now maybe it's like not naturally that we very
yeah, that's part of it, and also like I'm a little bit hesitant as well to like try to attribute too much perturbation theory logic to what goes on here. Certainly in the right limit, that's a totally sensible thing to do, and I think that's something I should look into it. I wonder if someone's already thought about it. Yeah.
I mean, if you want to do loops, right? It depends on what else is there. Because ATS 5 can something else.
Yeah.
It will depend on the something else.
Yeah.
Right? And there are many choices. There's something else and there's many different things.
Yeah, for instance, if you insist there are no other light priorities, let's say pure gravity, somehow we can see an inconsistency. That would be saying pure
It's good gravity depends that you will see that there.
But in the boundary, will you see that you cannot, you somehow find the link? There seems to be some suggestion of that kind. You find that central charge.
Yeah, because he said that there is that you have to that corner exists only in C for you. Right?
Yeah.
Yeah, but does the corner approximately exist in perturbation theory one of C?
I can't answer the perturbation theory question, but I can just say that I put in like a central charge of like 1,000 or 1,000,000 or something, and it immediately cut off this thing. So Or it cut it off, meaning that there has to be something lighter than dimension 6 in the parity even sector and lighter than dimension 7 in the parity odd sector. Could be, could be, could be. Yes. Yes.
The question is that you have to introduce an operator that you can't identify as a stress tensor, a double trace of stress tensor without just an derivative anomalous dimension. But that would be already a very strong statement. Sure.
And you actually, if this really pure, then the massless sector will be just pure gravity, and then there will be that's what matters.
Yeah, so it would show you that the string coupling, you would have to see a string at some point, before 1 over n square. For instance, let's say you could show that you had to introduce another like primary operator at a dimension that was less than n.
So that's string scale.
Yeah. So it will show you that you have to have a string. This I didn't understand what you just said, because clearly when you have TTN, when you have finite TTP, you get anomalous dimension. So these other operators you're talking about, the one you wrote there, the dimension is not just the engineering dimension, the dimension is not 6.
That's right.
The dimension is 6 minus something.
That's right. That's right. That's right. That's right.
So then it happens to be a pure TTN. You'd say that's not a pure stress tensor theory. You say pure stress tensor means everything is free.
Well,
you say that you allow small activity connections and pure gravity.
At the level of axiomatic CFT, there's not really a clear notion of what a pure stress tensor theory even is, because you don't know what your operators even are at the level of some Lagrangian you might have written down in the UV. The only thing that you can see are the pure IR observables. And so the only thing I can say is just that you can write on one pure stress tensor theory, which is this mean field theory that's trivial, factorizes all these things, and where these dimensions are exactly the same as their engineering dimension. And certainly you can come up with a theory that is ever so slightly off from this mean field theory that has some anomalous dimension, things like this. I don't know how I would be able to tell whether that's a pure stress tensor theory or something else.
Let's say central charge is 100.
Yeah.
You actually found at some point you had to introduce an anomalous dimension of 1, which wasn't 1 over 100.
Yeah.
You'd see immediately you'd have to introduce a new operator. I mean, I
Sure.
agree.
But anomalous dimension of 1 would probably not string scale. No, I would think that what
you have to go to high one. So I agree that you have to make it precise, because you have to go to, but
it has to be heavier than 3 gravity.
that's it. Heavier than 3 gravity, heavier than 3, maybe even higher.
Yeah.
But let's say you at a central charge of 100, you found that in fact you introduce a new light operator at 10, well below 100, well below dimension 100, even though the central charge was 100.
Yes.
That would be the statement you have to introduce a new
String segment.
Yeah. In fact, this CMZ, you could formulate the CMZ logic in this way, right? You could say that CMZ, say if you have high derivative corrections. So high derivative corrections actually take your 3-point function. They tell you what parity odd and parity even structures can be. So what CMZ roughly says, if you think that 3-point functions look like one line and have a correction, that's not blank scale, but that's separate for some other parameter. Then in fact, you need to add an infinite number of parameters, infinite number of like fields in the bar. Trying to do the CMZ thing in the bootstrap, like this time delay story, Shapiro time delay story. You don't have to know that.
Yeah, I'm familiar a little bit, but I'm not by no means an expert.
Is that if you add high derivative corrections that have a large parameter, like we have in string theory, string theory does a G-split. So the high derivative corrections are not blank scale, they appear at low scale. Then you also have to introduce new particles. In this statement, it must be the statement that if you do 3-point function and you correct it, so there's a pure gravity 3-point function. Which you compute. But then you add some corrections to it, which are controlled by some other parameter. Then you will find that you need to add a new light primary operator. At a dimension much lighter in the sense, like much below the blank scale. And in fact, you can probably even predict where.
I see. But would it be lighter than 6 and 7?
No, the 6 and 7, I think, is the anomalous that. So the parameter mapping is controlled compared to string scale, which maybe your central charge is 100, so blank scale might be 100. Maybe string scale is 20. find that if you change the 3-point function and you added a correction of size 1/20, you have to add a new particle at size 1.
Yes. The well,
Really have a large ADS, right? Then the string scale states will be much higher than multi-diagonal.
Much higher than multi-diagonal, but much lower than Planck scale.
Planck scale, right?
So Planck scale is hundreds. And so we added correction to the 3-point function, which is not, so the 3-point function anyway 1/100.
Yep.
But now I added a correction which looks like 1/100 into 1 plus 1/20, not 1 plus 1/100. So now what I'm saying is string scale is 20. Planck scale is 100. And then at 20, you will find you have to add new parts. It's not at 100. Well, you have to add 1 at 20 and 1 at 20 and so on. That's roughly the result.
yeah.
That is not impossible.
No, it doesn't seem impossible, except that the reality of the numerical bootstrap as well, I should say. So going back to this extremal spectrum that I'm showing here, this is a zoomed in version, but the very heavy operators are very suppressed in the numerical bootstrap. They don't play. Yeah. So it's not only are they suppressed, but they're a little bit imprecise. So like you have this huge noise of operators here, let's say. This is even at just dimension 5 or twist 5. Those operators, it's numerically speaking, if you have 2 operators that are right next to each other or 1 operator right in the middle, those are somewhat equivalent solutions to each other as far as the numerics is concerned. So it's not something that the numerics would be able to say anything about, unfortunately. The large dimension, like, yeah, the where it works best is for the leading twist and leading dimension operators. So I don't know to what extent we would be able to say anything conclusive, because it's just so hard to determine what's going on up there. It's yeah.
If there are no further questions, then let's thank Rajeev again for the really nice talk. Thank you.
Okay.